Okay, we're now looking at page 25, just continuing from halfway down. De Moivre's theorem. We use De Moivre's theorem to work out what our complex number with powers is. So, for example, we know, and this is just the proof of De Moivre's theorem. Now, if Z1 equals R1 cis theta 1 and Z2 equals R2 cis theta 2, then we know from what we did on previous pages that Z1 times Z2, to multiply two complex numbers, we multiply the moduli and we add the arguments. So it's R1 times R2 times cis of theta 1 plus theta 2. Now, if Z1 happens to equal Z2, which is equal to Z, which equals R cis theta, then we would end up here. We would end up with basically R cis theta times R cis theta. So if Z1 equals Z2, which is equal to Z, which equals R cis theta, then Z squared would be R cis theta times R cis theta, which is R squared, and so that would be R times R, and then we do, cis theta plus theta, which is R squared cis 2 theta. Now, similarly with Z to the power of 3, that's the same as Z squared times Z. Now, using our result from this line here, that's R squared cis 2 theta times R cis theta. Remembering we multiply the moduli, so that would be R squared times R, and then we'd have cis 2 theta plus theta. So we've got R cubed cis 3 theta. Now, if we continue, notice Z squared is R squared cis 2 theta. Z cubed is R cubed cis 3 theta. So therefore, in general, if n is a positive integer, then Z to the power of n is R to the power of n cis n theta. And this is known as De Moivre's theorem. So therefore, De Moivre's theorem is, if Z equals R cis theta or R cos theta plus I sine theta, and n is an integer, then Z to the power of n is equal to R to the power of n cos n theta plus I sine n theta, or it's R to the n cis n theta. Okay? So that's De Moivre's theorem. Now, if our complex number is in the modulus argument form, we can, so if your complex number is in mod arg form, and if together using De Moivre's theorem, we can have a very convenient method and a simple method for calculating positive and negative integral powers of a complex number. So for example, we could do Z to the power of 5 or Z to the power of minus 6, etc. Okay, so they need to be integers. So integral powers are powers that are integers, okay, which is positive or negative whole numbers and 0. That is the definition of an integer. Okay, now we're going to move over now to page 26. Question, we're asked to express 1 plus root 3i all to the power of 6 in x plus yi form, in other words, in Cartesian form. So before we can apply De Moivre's theorem, this needs to be expressed in modulus argument form. Okay, so you've got a few ways of expressing this in modulus argument form. We can just sketch where 1 plus root 3i is on the complex plane, and it would be 1 and this would be root 3. And we can just say that r is modulus of z, which is the square root of x squared plus y squared, which is the square root of 1 squared plus root 3 squared, which is the square root of 4, which is 2. And tan theta is root 3 on 1, which is root 3. So therefore theta is 60 degrees, which is pi on 3. So therefore 1 plus root 3i can be expressed in mod arg form as 2 cis pi on 3, or 2 cos pi on 3 plus I sine pi on 3. Now using De Moivre's theorem, we've got that, we've got 1 plus root 3i to the power of 6 is the same as 2 cis pi on 3 to the power of 6, which is 2 to the power of 6 cis 6 pi on 3, because it's 2 to the power of 6 and then cis of 6 times your angle there. Now, 2 to the power of 6 is 64. Now we need to expand our cis 6 pi on 3. 6 pi on 3 is 2 pi. So it's cos of 2 pi plus I sine 2 pi. Now, the cos of 2 pi, just drawing, looking at your curve, cos of 2 pi is 1. If you just look at your cos curve, it's like that, it's 1. And sine of 2 pi is 0. So it's 1 plus 0i. So therefore 1 plus root 3 to the power of 6 is equal to, so that equals 64. Now I can just go back here, just one sec. We know that if I want to put this in mod arg form, that's 2 to the power of 6 cis 2 pi. And remember that principal argument has to be between negative pi and positive pi. It's the same as 2 to the power of 6 cis 0. But look, cos 2 pi is the same as cos 0. Sine 2 pi is the same as sine 0. So you can just go straight from there, okay? So the answer to that question there is 64. Okay, the next question, example 2, if z equals 1 minus I, express z to the power of minus 7 in Cartesian form. So first you need to express 1 minus I in modulus argument form. Look, let's just sketch where it is. We've got 1 across and 1 down. So we've got 1 and 1 because this is 1 minus I, or 1 minus 1i. Okay. Now we know that that's in quadrant 4, and it's an isosceles triangle. So this angle here is 45 degrees. But let's just do r is modulus of z, which is the square root of x squared plus y squared, which is the square root of 1 squared plus 1 squared, which is the square root of 2. We know that tan theta is 1 on 1, which is 1. Therefore, theta is, because we're in quadrant 4, it will be minus 45 degrees, or minus pi on 4. Okay? So therefore, your complex number, z equals 1 minus I, is root 2 cis minus pi on 4. So therefore, 1 minus I to the power of negative 7, or z to the power of negative 7, we may as well just write. So therefore, z to the power of negative 7 is root 2 cis minus pi on 4, all to the power of negative 7. Now, applying De Moivre's theorem. So using De Moivre's theorem, z to the power of minus 7 is equal to root 2 to the power of minus 7 times cis of negative 7 times minus pi on 4, which is 1 over root 2 to the power of 7 cis positive 7 pi on 4. Now, 7 pi on 4 is bigger than pi, so we need to sketch where that is. So just a quick sketch here. 7 pi on 4 is 1 3/4 pi. So we know that 7 on 4 is 1 3/4 as a mixed numeral. And we know from here we've got 0 all the way around. That's 2 pi. So this is pi. This is 1 1/2 pi. So 1 3/4 pi would be 1 1/2 would be here, somewhere there. So 7 pi on 4 would be there. But remember, we're going to subtract 2 pi from this so that we've got the principal argument. So we're just going to look at 7 pi on 4 minus 2 pi. So on your calculator, just do 1 3/4, or 7 on 4 minus 2. That's like 1 3/4 minus 2 is negative 1/4, so it's negative pi on 4. So that's the same as, now so it'll be cis negative pi on 4. Okay, now root 2 to the power of 7, root 2 squared is 2. So you're really doing that 3 times. So you get 2 times 2 times 2 is 8. So you get 8 root 7 here on the denominator here. Because root 2 times root 2 is 2. Then you get another times 2 and another times 2, and you've still got a root 2 left over. So now expanding this, we've got 1 over 8 root 2 cos of minus pi on 4 plus I sine minus pi on 4. Sorry, just let's just keep this all separate here, which is, sorry, I just ran out of room there, so I've just moved it over, which is 1 over 8 root 2. Now this is cos of, this is minus pi on 4 here. Okay, so this is 45 degrees, so it's in quadrant 4, cos is positive, so it's the cos of 45 degrees is 1 on root 2, but in quadrant 4 sine is negative, so sine of negative 45 is minus 1 on root 2, so it's plus I times negative 1 on root 2. Now expanding that, we get 1 over 16, so it's 8 root 2 times root 2 is 1 over 8 times 2, which is 1 over 16. Then we've got minus, and here we've got minus I over 16, okay? Minus 1I on 16, or you could, yeah, so you can just leave it like that, or just minus I on 16, okay? Because we're doing 1 over 8 root 2 times negative I on root 2, and we get minus 1 on 16. And that's it for that question there. Now for example 3. Now it says to simplify that expression there. Simplify root 3 minus I over 9. So root 3 minus 1 to the power of 9 over 1 plus I to the power of 5. Now the first thing we need to do is write each of those in modulus argument form, and then we can apply De Moivre's theorem to each of those, okay? So let's just look at root 3 minus I. I mean, we can use, if we want, the that alternative method where we're saying so if I put them both over 2 and put a 2 here, so I'm just using exact values, okay? So I've got root 3 minus I. You can do it the other way, but I just thought I'd do it this way. That would be 2 times root 3 on 2 minus I on 2. Now, cos of what is root 3 on 2? It's cos of 30, and sine of 30 is also a half. But the problem here is we've got a minus, so we must actually be talking about quadrant 4, because cos of 30 is equal to cos of minus 30. This is telling us that we're quadrant 4 here because we've got minus I on 2. So the plus I sine theta, you're getting a negative answer for that. So the acute angle is 30 degrees, but we're in quadrant 4. So therefore this will be 2 cos minus 30, which is minus pi on 6, plus I sine minus pi on 6, okay? Which is just 2 cis minus pi on 6, okay? So that means that root 3 minus I to the power of 9 is 2 to the power of 9 cis minus 9 pi on 6. Now I'm just going to keep that as 2 to the power of 9 cis. Now 9 pi on 6, that's minus 3 pi on 2. Okay? So, but that minus 3 pi on 2 is still not a principal argument. So that's the same as 2 to the power of 9 cis. Now, remember, you can either add 2 pi or subtract 2 pi to this. If I don't want to subtract 2 pi because I'll end up even further back. I'll go further back. I need to add 2 pi to this. So this is minus 1.5 plus 2 gives me plus a half, which gives me the same as pi on 2. Okay, so that's our numerator in modulus argument form, and then applying De Moivre's theorem. Now with the denominator, 1 plus I to the power of 5, this would be either I'm going to do root 2, yes, I'll do root 2. So we've got root 2, 1 over root 2 plus I over root 2. Sorry, I'll just do the 1 plus I first. So that is root 2. Now, cos of 45, we must be in quadrant 1 here because both cos and sine are positive, and we know that cos of 45 equals sine 45 equals 1 on root 2. So it's cis pi on 4. Okay, so therefore 1 plus I to the power of 5 is root 2 to the power of 5 cis 5 pi on 4. Now 5 pi on 4 is beyond pi, so we're going to, because it's bigger than pi, we'll subtract 2 pi. So we've got 1 1/4 pi minus 2 pi is minus 3/4 pi. So it's minus 3 pi on 4. Now root 2 to the power of 5, every root 2 to the power of 2 is 2. So we've got 2 times 2 is 4. You'll have 4 root 2 cis. Sorry, I forgot to put the cis there. Sorry about that. So we've got root 2 to the power of 5 cis to the minus 3 pi on 4, which is 4 root 2 cis to the minus 3 pi on 4. Okay, so now we've expressed them both in modulus argument form and applied de Moivre's theorem. So now we're going to look at division of complex numbers. So we've got root 3 minus I over to the power of 9 over 1 plus I to the power of 5. That will be 2 to the power of 9 cis pi on 2 over 4. Actually, I could keep it as 2 squared, but that's okay. 4 root 2 cis to the minus 3 pi on 4. Now remembering when we're dividing complex numbers, we divide the moduli and we subtract the arguments, okay? So 2 to the power of 9 over 4, that's what I'd be doing first, and then just throwing your root 2 down there. Or actually what I'm going to do is actually rewrite this one here. So I've got 2 to the power of 9. Now root 2 to the power of 5 is the same as 2 to the power of a half. So that's the same as 2 to the power of a half to the power of 5. And then what we're doing, I'm just rewriting this, okay? Cis pi on 2 over cis minus 3 pi on 4. Now that the bases, so this is 2 to the power of 9 over 2 to the power of 5 on 2, so you just do 9 minus 5 over 2 gives me 13 over 2 for this. Just one sec. Sorry about that, I'll just fix this up. Sorry, I'm not sure how long that was on the screen, that message, so I'll just go over this again. We've just moved root 3 minus I to the power of 9 is 2 to the power of 9 cis pi on 2, so I've just written that there. 1 plus I to the power of 5 is 4 root 2 cis minus 3 pi on 4. Just looking at this now, I'd rather write this here, root 2 to the power of 5, as 2 to the power of a half to the power of 5, which really is 2 to the power of 5 on 2. Because when bases are the same, you can just subtract the indices, okay? So remember, we're dividing the moduli, so we're doing 2 to the power of 9 divided by 2 to the power of 5 on 2. Now that's 2 to the power of 13 over 2. And we've got cis. Now what we do is we subtract our arguments. So we've got cis pi on 2 minus 3 pi on 4. Now 2 to the power of 2 to the power of 13 on 2 is 2 to the power of 6 times root 2. And here we've got cis. Now we've got a half pi plus 3/4 pi, so you can just do a half plus 3/4 on your calculator, and we get 1 1/4, which is 5 pi on 4. Now that is not a principal argument, so you need to subtract 2 pi from that, so 5 pi on 4 minus 2 pi. Now that's 1 1/4 minus 2, which is minus 3/4. So therefore, 2 to the power of 6 is 64. So we've got 64 root 2. And I'm going to open this up now. Cos of minus 3 pi on 4 plus I sine minus 3 pi on 4. And just evaluating that, we've got 64 root 2. Now minus 3 pi on 4 is over here with a related angle in here of pi on 4. Okay, if this is minus 3 pi on 4, this is, so if you've got 3/4 pi, you've got a 1/4 pi here, because from here to here is minus 1 pi. Okay, so we're looking at the related angle here is pi on 4, or 45 degrees. We're in quadrant 3, cos is negative, so this is the same as doing minus cos of pi on 4, and again sine's negative here as well. minus I sine pi on 4, which is 64 on root 2, negative 1 on root 2, minus I times 1 on root 2. Sorry, just running off the screen there. And just, sorry, that's 64 root 2. So I'll just fix that. So therefore, multiplying that by that, we've got negative 64, and multiplying these, minus 64I. And if you want, you can take out, now that's in Cartesian form, okay? Or I could write that as negative 64 bracket 1 plus I, okay? All right, that's the end of page 26. Next question, example 4. So we've got let Z1 equal 2 cis pi on 3 and Z2 equals root 2 cis pi negative pi on 4. Find the smallest positive integer n for which Z1 over Z2 to the power of n is a real number. Now, before we start, we're going to have to come up with an expression for Z1 over Z2 to the power of n. Now, for Z1 over Z2 to the power of n to be a real number, then remember it's a complex, this is a complex number, and De Moivre's theorem would be applied. But if it's a real number, then there's no imaginary component. So therefore you'll be doing I times 0. Okay, so what we need to do is we need to make sure that the argument of Z1 over Z2 is 0. Okay, so that is the only way that Z1 over Z2 to the power of n is going to be a real number. Because if you've got x plus yi, and that would be the complex number that you end up with, for it to be real, then there is no imaginary component. So what we're going to do, we're just going to look at the argument of Z1 over Z2. To do the argument for Z1 over Z2, we need to do, well, I'll just do that here. Sorry about this, I'll just rub that off. So, the argument of Z1 over Z2 is, the way we do that is we would subtract the arguments. So it'd be pi on 3 minus negative pi on 4, which is pi on 3 plus pi on 4, which would be 7 pi on 12. Okay, now 7 pi on 12 is a principal argument because it lies between negative pi and positive pi. Okay, now the argument of Z1 over Z2 to the power of, to the power of n, just looking at the argument of that, that would be 7 pi on 12 times n, which is 7n pi on 12. Now, we need this argument to equal 0. Sorry, no, we don't need the argument to be 0. What we need is for sine of 7n pi on 12 to be 0, okay? Because if we look at our complex number, I'm just going to write it here. So Z1 over Z2, remember we divide the moduli, would be 2 over root 2. We've already subtracted the argument, so you'd get cis of 7 pi on 12. So therefore, Z1 over Z2 to the power of n, remember, 2 on root 2 is just root 2, okay? So that's just root 2 cis 7 pi on 12. So therefore, Z1 on Z2 to the power of n is root 2 to the power of n cis 7n pi on 12, just as what we wrote up there, which is root 2 to the n cos 7n pi on 12 plus I sine 7n pi on 12. Now, the only way that this is going to be real is if, so this will only be real, so Z1 over Z2 to the n is real if will only be real if sine of 7n pi on 12 is equal to 0. Now, if I draw the sine curve here, okay, the only time that sine of anything is 0, we know that sine of 0 is 0, sine of pi is 0, and sine of 2 pi is 0. So the only way that we will get 0 here is if we've got integer multiples of 0. So z1 over z2 to the power of n is real if sine of 7n pi equals 0. Or we can say if sine of, actually what I'll write here is, we know that sine of n pi equals 0, where n is an integer. So therefore you need integer multiples of pi. Okay, so thus making our imaginary part here equal to 0. Now, the first time we will get an integer, the first time that we will get something like 7n pi on 12 equaling something like this. So if I look 7n pi on 12 to equal an integer would be if n was 12, because we're trying to cancel out the denominator of 12. So if n equals 12, we get 7n pi on 12 is 7 times 12 pi on 12, which happens to be 7 pi. And that would be the first time that this 7n pi on 12 will give me an integer, a whole number there. It'll only happen when the n is 12. The next one will be when n is 24, okay? And then n is 36 will give us the next one. Or you could go back in the negative direction and get negative 12, okay? For a, if we want to look at the other direction, okay? But we were told that n, we had to find the smallest positive integer n, for which that is a real number. And so therefore, n equals 12 will be the answer to that, okay? Is the smallest positive integer, for which that expression there is real. Now in part B, it says if z equals z1 cubed over z2 to the power of 5, find z in Cartesian form. Now this is just fairly straightforward. So part B, if z equals z1 cubed over z2 to the power of 5. So that's what we're trying to find, z1 cubed over z2 to the power of 5. Okay, now z1 is 2 cis pi on 3. So we can just apply De Moivre's theorem. Okay, so z1 cubed is 2 cis pi on 3 cubed, and z2 to the power of 5 is root 2 cis minus pi on 4 to the power of 5. So this is 2 cubed cis 3 pi on 3 over root 2 to the power of 5 cis minus 5 pi on 4. That is applying De Moivre's theorem, okay? Now dividing here, so therefore that is equal to, remember we divide the moduli and subtract the arguments. This is really 2 cubed over, now root 2 to the power of 5, that's 2 to the power of a half to the power of 5, that's 2 to the 5 on 2. And we've still got, now cis 3 pi on 3 is just cis pi, and here cis of minus 5 pi on 4, that is not a principal argument, so we need to add 2 pi to that, so it's minus 5 on 4, which is minus 1 1/4 plus 2, which is positive 3/4 pi. So first we're doing them as principal arguments, okay? So now we'll apply our division. So this is using De Moivre's theorem. This is writing these both as principal arguments. Now we need to divide the moduli. So 2 cubed over 2 to the power of 2.5 is obviously 2 to the power of a half, which is root 2. Okay, so I'll just write that as root 2. And then we've got cis, then we have to subtract the arguments. So we've got cis pi minus 3 pi on 4. So we get root 2 cis. Now pi, which is 1 minus 3/4, is a quarter. So it's cis pi on 4. Now that is a principal argument because it lies between, between 0 and, between negative pi and pi. So now that is root 2 cos of pi on 4 plus I sine pi on 4 which is root 2 times 1 on root 2 plus I on root 2. And expanding that, we get 1 plus I. Okay, that's the end of the examples up to the end of page 27. I'm going to stop this video now. The next video will be pages 28 to 30.